Hello, AP Calculus AB students, and welcome back to your Topic 1 lessons on limits and continuity. Today's lesson is a heavy focus on, based on the title, continuity. Our daily learning objective is to use the 3 criteria for continuity to analyze continuity at a point. We're going to dive pretty deeply into that sentence on the second page. Our first page, though, is a nice little opener. It's nothing we've quite done before, but I think as a connection it shouldn't be too terrible. So we have 2 piecewise functions for the opener. We're going to be doing a lot of piecewise functions today. And as we're looking at these 2 piecewise functions, you'll notice that each of them have 2 branches, 1, 2, 1, 2. But in those branches they also have this constant b, where we're going to have to identify a value for b and decide how or what will that value be to make this piecewise function continuous. To give you somewhat of a visual of what's going on here, and I'm going to erase this, so no reason for you to draw it. Here's my xy axis. 3x plus b is a line, right? This is mx plus b. So we know b is something on the y-axis, and it has a slope of up 3 over 1. We also know, though, that this line is only going to exist for x is less than or equal to 2. So here is 2. This entire side is where x is less than or equal to 2, and we're going to have some sort of line with a slope of positive 3. So my line could look like this, it could look like this, or like this. We don't really know where the line is, right? Then we also, let's just keep maybe one in the middle here, maybe it looks like this, who knows. Then we also, that's going to be this one up here, have a second line, which is x minus 2, and that one's fully graphable, right? 1, 2, looks like this, and the slope is up 1 over 1, up 1 over 1, up 1 over 1. But it's only good for x is greater than 2, which we know is on this side, and so it would look something like that. Okay, that can't be equal to 2, so we have an open circle here. That wasn't great. Second try. An open circle here. This one can be equal, closed circle here. All right, and if we asked you about the limit as x approaches 2, and I picked 2 because that's where our 2 functions come together, would the limit exist here? And hopefully you'd look at that and say, well, no, there is a jump discontinuity. As we trace this, and I get to here, I have to pick up my pencil, skip over the open circle, and then trace over here. So we know that that has a limit that does not exist, right? We approach from 2 different sides. Your job, though, is to figure out the value of b that would make these 2 functions come together. Now, in order to do that, what you're really going to want to look at are one-sided limits. Because what we're trying to find is, when are these limits equal? So to set this up, we're going to go through, and I'll keep my red and my green separate. We're going to find the limit as x approaches 2. Let's see, the red functions for x's that are less than 2, so it's approaching 2 from the left side of f of x. And we're going to find when is that limit equal to the limit as x approaches 2 from the right side of f of x. You have all the mathematical tools to figure out what the left side and right side should be. There's a little bit of algebra in there as well, but I'd like you to consider starting each one of these problems like so. So I'm going to give you a minute or two to try these 2 problems. Once you've tried it, unpause. We'll see how you did. We'll discuss notation and jump into our main theme today of continuity. So again, what makes those 2 limits equal to each other to make the overall limit exist? Ready, set, go. All right, well, you're back. Let's go ahead and work through this. So I started with f of x on both of these. Notice I didn't skip right to the equation because we want to discuss the overall function, which is this guy. Once we're here, now we can actually replace f of x with what it's equal to. And for x is less than 2, or on the left side of 2, it's equal to 3x plus b. Then on the right side, my limit as we approach 2 from the positive side of f of x is the function x minus 2. The right side is pretty easy to evaluate as well. We just take this x of 2 and we substitute it in for x. The positive doesn't make a difference because this is going to have the same value whether it's on the left or the right of 2. So we just substitute in. We don't need the limit anymore, and hopefully we can see that that becomes 0. On the left side, similar idea, but this is as x approaches 2, so we need to replace the x with 2 and keep the plus b. So this becomes 6 plus b. At this point in time, we can go ahead and isolate b. because now we just have a basic algebraic equation where we're interested in the value of b, and of course to do that we just subtract 6 from each side, and that will give us that b equals -6. So if b equals -6, then what is the overall limit? Well, if b equals -6, then the left and right side limit should be exactly the same. The right side was 0, which means the left side better be 0. And I'll just check that really quickly over off on the side, right? If I was doing 3 times 2, and then we said b was -6, 6 minus 6, I think that is 0. The left side 0, the right side 0, therefore the overall limit is 0. Okay. Again, it might be nice to have a visual of what happened here, so I do have all the graphs prepared. This is our first problem on the opener. Let's see our two equations. We'll zoom in a bit. There we go. So I have this equation, 3x minus 6, this one x minus 2, and you'll notice that right when x is 2, my left side equation and my right side equation approach the same spot. They both approach 0. And that's all we showed right here. So let's try our next one just to make sure we have this concept down. I'll do the same thing. We'll do red up top and green down below. We're going to find the limit as x approaches where this time? -1 from the left side, and less than -1 is my red equation, x squared minus 5x. And I already did what I said you shouldn't do. I'm going to start with f of x. Oops, there we go. Equals, and we'll do the right side. The limit as x approaches -1 from the right side of f of x. From here, I'll actually replace these, maybe write a little bit smaller so I don't quite run out of room. X squared minus 5x, and same thing on the right. I think it's important to practice all the way through this notation. I'll show you what some students tend to do, and they probably wouldn't receive full points for this if it was on the free response section of the exam. What some students like to do is they like to skip these first two steps, and even worse, I'll show you the real bad thing that would definitely not get you points. They would say, oh, x squared minus 5x needs to equal bx cubed minus 7. As soon as you write that, that is incorrect. These two are not equal to each other, right? This is a parabola, and it does its own parabolic thing. This is a cubic function, and it does something like this. They are clearly not the same graph. Now what we're going to do here is we have the limits out front. So we're not saying the two graphs are the same. We are saying that the two graphs have the same value for the limit at one specific point. And at what point? Well, we're going to replace the x's with -1. And it looks something like this. B times -1 cubed minus 7. This is a true statement. This is not. Because what we're doing here is we're trying to say the two equations are the same when x is -1. Up here you're saying the two equations are the same everywhere, and that's a no-go. As soon as you write that, you would definitely lose a point. Some students like to skip down to here. I think you probably would also not earn full points there because you didn't show us how you entered into the problem. You didn't show the setup, and so my guess is you would have to show either this or this. Probably better to show this first step, then you could maybe go to here. But again, entering into the problem is where you start to earn points, and if you don't enter in, usually they won't grade the rest of your problem. So you need to show the starting point, and the starting point, shockingly in calculus, generally needs to include calculus. That means a limit, a derivative, or an integral, and you don't know those two, so pretty much every starting point for this first unit better have a limit somewhere. Okay, let's simplify this down. This is +1 plus 5, which is 6. And on the right side, we have -b, right, -1 cubed minus 7. Okay, I'm going to add b to the left side. That'll make b positive. And then I'll subtract 6 from the right side. -7 minus 6, I think, is -13. So if b is -13, then the limits better have the same value. This left-sided limit is 6. If b is -13, then that's going to have the same value. Can you see -13 is 13 minus 7 also gets you 6, so their value better be 6. And we'll double check the graph just to make sure that I haven't done this incorrectly here. Here's my cubic graph. We're looking at -1. There it is. Oh, look. As we approach from the right side, we approach this point right here, and from the left side we approach 6 as well, right? Getting closer to 6 from both sides. You'll notice the red graph had an open circle because there's no equal to, versus the black graph had a closed circle because there is an equal to. All right, nothing too bad. So let's go ahead and quickly sketch and compare the two graphs below. Now, you might say, well, these two graphs look pretty darn similar, right? 3x minus 6 for x is less than or equal to negative 2, and x minus 2 for x is greater than 2. And over here, right, we have the exact same equation. So maybe if we sketch one, the other will be the same. And we've actually done this before, right? This is problem 1 up above. So let's go through it pretty quickly. We have 2, so I always like to do that little wall here, right? And then 3x minus 6, we know it's less than 2. So I'm just going to cheat and say, well, negative 6 is down here. And then it's up 1, 2, 3 over 1, up 1, 2, 3 over 1, and it can be equal to 2, so it looks like this. And here is my first one. And then the second one is x minus 2. I'm not actually going to start there, but I am just going to go up 1 over 1, up 1 over 1. Oh, cool. I'll do the open circle kind of on top of it, even though you would just see a closed circle, and up 1 over 1 like so. Not too bad. Now, knowing that first one, can you see what the second one's going to look like? Pretty darn similar, isn't it? Do you see the only difference? Well, the only difference, and I'll highlight it in purple here, is that this guy has an equal to, and this one does not. Which means the two graphs are exactly the same, but right at 2, neither of them is equal to 2, so there's just going to be an open circle right here. And that was a very poor open circle. There we go. And down 1, 2, 3 over 1, down 1, 2, 3 over 1, like so. So here is one part of it, and here is the other. There we go. So they almost look the same. The only difference is at one specific point when x equals 2. So a quick question. How could you explain why f of x, that's this one up here, is continuous at x equals 2, while g of x is not continuous at x equals 2? And think about different ways you could explain it. Could you explain it to a 5-year-old, an Algebra 1 student, someone in calculus? So think about those explanations, and then we can maybe jot down a few ideas as well. Okay, so if we're talking continuity, to a 5-year-old, it's actually pretty easy, right? To a 5-year-old, you would probably show this graph and you would leave off this open circle right here. And to a 5-year-old, you would say, well, as you're drawing or walking, you have to pick up your pen or pencil and skip over that gap, right? So you just walk and there's a hole, no good. To an algebra student, you might really have to do the same thing. To an algebra student, you could say, oh, there's an open circle there. They learned those in Algebra 1. So an open circle means we're not continuous because you have to pick up your pencil, right? And then to a calculus student, it gets a little more interesting because calculus, we bring in the idea of limits. But that doesn't really seem to help us here because both of these have the same limit. As we approach 2 from both sides, that limit is, as x approaches 2, is 0. And over here, the limit is also 0, right? As you get closer and closer to this point, you both approach 0. It doesn't matter if there's a point there or not because limits don't talk about a point. So if we've only learned limits in calculus, it seems like they haven't done a good job of discussing if a function is continuous at a point. But they are involved. And in fact, there are 3 criteria that you need to discuss and memorize when we're addressing continuity at a specific point. And here's what it looks like. A function f is continuous at a point if and only if all of the following are true. So the first thing we need to make sure happens, and this is what didn't happen on the other page, is that f of a exists. Right? So f of a is like your y value. And if f of a exists, it really means that a, whoops, that's supposed to be an a comma f of a is on the graph. Now what is a comma f of a fancy way to say? There's no limit here. This is the actual point, right? So if we look up here, the a comma f of a comma f of a is in this point. If we were to substitute in 2 to our equation, this would be does not exist, right? There is no point there. and that's no good. So if you substitute in the value that they're asking about and there's nowhere to plug it into the piecewise function, we can't use 2 here, can't use 2 here, then there's no point, then we know automatically the function's not continuous at 2. However, if we want the point to exist, and this is on the graph, then this is really just a fancy way to say a comma f of a is on the graph. The point at x equals a exists. And so if you are proving this, and this is a very common free response question, if you're proving this on a test, then you will need to state somewhere that f of a equals something. You'll need to do the math. You'll need to show that you plugged in a to the equation. So we'll say substitute a in for x, right? You plug it in, do the math, and show that there is an output. And so the nice part is if they had asked us if this piecewise function was continuous at x equals 2, you would just say that g of 2 does not exist. And then you'd say, therefore, not continuous. All right, but that's not enough, because just having a point there doesn't mean a function is continuous. What also has to happen is that the limit as x approaches a of f of x also has to exist. The most common way that you show the limit exists is you show the two one-sided limits, just like we did on the opener. Okay, so in order to do that, so in words, you need to prove the limit exists, and I'll say usually using one-sided limits. So if it's that piecewise function that does something different on each side, you would find each separate side, substitute in your value a after setting up the limit, and make sure that they're equal. That's all we're saying over here. We'd show the one-sided limits are equal, and then you can say, therefore, that triangle, right? Therefore, the limit as x approaches a of f of x exists. Now, last but not least, we need one more thing to happen. And that one more thing is that although the limit has to exist and the point has to exist, what if they were in two different spots? Can you visualize that graph, right? If we had a limit that exists, you're still not continuous, and then you had a point that exists, that meets the first two criteria. Point exists, limit exists, but that's not continuous. You have to pick up your pencil. So the third thing is that this point better be in the same spot as the limit. And the way that we say that is that f of a equals the limit as x approaches a of f of x. So we'd say the point is equal to the limit. And the nice part is if you've done step 1 and step 2, you've probably already figured out step 3. Because you did the math on step 1, you found the point. You did the math on step 2, you found the limit. If 1 and 2 have the same value, then the third thing you just state is the point equals the value, therefore continuous. Now, when a question asks you to show that a graph or an equation or anything like that is continuous, or the opposite of continuity, discontinuous, you do need to go through all 3 steps. The 3 items known above are known as the 3 criteria for continuity, 1, 2, 3. So let's make sure we can do the opposite first. Let's understand why each of those had to be there for our function to be continuous, and then we can move on to some practice. So, reason number 1. If we're going to sketch a graph that breaks continuity because of reason number 1, and again, reason number 1 is that a point doesn't exist, let's do something that is almost continuous, and I'll just do a cute little wavy line here, like so. Okay, this limit exists, so step 2 is fine. However, this is not continuous because there is no point at, and I'm going to call this a right here. So reason number 1, we would say f of a does not exist. And again, visually you can see you have to pick up your pencil, but that is not mathematically rigorous enough for the AP exam. You can't say, oh, you have to pick up your pencil, it's not continuous. You have to reference one of these 3. All right, reason number 2. Well, let's tackle reason number 1 first and make sure that that's okay. So reason number 1 is that there needs to be a point. So let's do kind of that same squiggle graph, and I'm going to put in a point this time, right? So we're looking pretty good. Except then I'm going to do an open circle, and move off there. Clearly this function is not continuous. You have to pick up your pen or pencil. And the reason why is that the limit as x approaches a from the left side of f of x is not equal to the limit as x approaches a from the right side of f of x. The limit overall does not exist. Okay, now let's look at the last one. I already gave you a graph for this last one, but show it once more and we can explain in mathematical logic up above what's going on. So we're going to go ahead and bring this limit together. That limit exists, that's step 2. We're also going to give this a point, that's step 1. There's a limit exists and the point exists, except the value of the point, f of a, that would be right here, is not equal to the value of the limit as x approaches a, right? That's down here. So this and this are not in the same spot, which is why you have to pick up your pencil. Just as a quick side note, a lot of times you'll see these phrases down below, and I think it's important to know what they mean. You do not have to memorize them. You're never asked to do this last part. You are asked to prove if a function is continuous at a point, and that's what we went through up above. But oftentimes they'll say, oh, this theorem only works, or this process only works if a function is continuous on an open interval. So we say that a function is continuous on an open interval, right? We don't include the endpoints, parentheses, if f is continuous at every value c on the interval a to b. So here is continuity on an open interval, and I'm just going to do kind of first quadrant graph to show you right now. Here is a, here is b. I'm going to do an open circle at a and then do the stereotypical math teacher graph like so. It's usually just a little squiggle, and I'm not going to worry about what's going on over there. There could be an arrow, open circle, closed circle. Continuity on an open interval, though, means ignore x equals b, ignore x equals a. This part in the middle is continuous, right? That part I just did in red. Doesn't matter that there's an open circle, closed circle here. This is continuous on an open interval. All right. Now what you could do, though it might take you a while, is you could take every single point on here and you can prove every point is continuous using these three reasonings, these three criteria up above. But nobody's going to do that. So if a question ever says it's continuous on an open interval, you know that any point between the endpoints meets those three criteria up above. Even more strict is continuity on a closed interval. Continuity on a closed interval now includes the endpoints, and they give you a little bit more specifics where they say, and we're going to go ahead and do something like this, a and b. I'm going to do something very, very similar. It's going to look like this, and then like this. Okay? And what they're telling you is that now we are not going to ignore it. I'm going to kind of underline and then circle here. As we approach a from the right side, okay, that is like this spot right here, the limit equals the point. And as you approach b from the left side, the limit equals the point. They're basically saying you do not have to pick up your pencil as you sketch from a to b. This is continuity on a closed interval. However, again, you don't need to memorize these. Just remember that if they give you an open versus a closed, they mean you can either sketch a graph without lifting up your pencil, including the endpoints, that's closed, and open is not including the endpoints. Now, this one was totally fine like the guy over here, but it doesn't matter if it works or not. You just can ignore them. All right, let's get into some actual practice for our last couple pages. All right. These problems are a combination of multiple choice and free response, and they're going to ask you to bring in those three criteria of continuity. And the biggest thing I'd like you guys to focus on, besides trying to understand the concepts, is that good notation. And again, we'll hit this with a hammer over and over and over and over again, just so we can make sure that you don't do anything weird and end up losing a point or two because of that notation. So let's begin. Answer the following questions about the graphed function f. We've got this cool little piecewise function going on over here. Use the definition of a continuous function, add a number to answer the following. All right, well, they've told us that f is not continuous at all these. We just need to explain why. So f is not continuous at x equals negative 7. So here's negative 7. You might say, oh, because you have to pick up your pencil. It is good to realize that is visually why it's not continuous, but the question becomes, which of the three criteria up here tells us what's going on down here? Well, the limit clearly exists. However, I don't see a point there, so to me, I would say f of negative 7 does not exist. There is no point at x equals negative 7. X is not continuous at x equals 2. Where is 2? 1, 2, that's right here. Well, let's see. I should switch colors, I think. I don't think we can say f of 2 doesn't exist, right? F of 2 certainly exists. So f of 2 equals, in this case, looks like 2. And I don't think we can say the limit doesn't exist, because the limit, as we approach 2, looks, oh, sorry, this goes up by 1/2, that's 1, isn't it? And this is 3. There we go. I think the limit as x approaches 2 from both sides of f of x equals 3. However, the third criteria of continuity is that the point and the limit are in two different spots, so I'm just going to say that those are not equal, and I think we should be good. Last but not least, f is not continuous at x equals 4, so 1, 2, 3 here is 4. Well, the point exists, right? F of 4 looks like it's negative 1. However, I think the limit does not exist. As we approach from the left and the right, we get two different values here. So we would say the limit as x approaches 4 from the left side, we'll do the top part first, looks like it approaches maybe 2.5, give or take. And then we would say that the limit as x approaches 4 from the right side looks like we approach negative 1. So we would say, therefore, the limit as x approaches 4 of f of x does not exist, right? We always want to show the two-sided limits or the one-sided limits to explain why the two-sided limit doesn't exist. There we go. Those are our three criteria. Point had to exist, limit had to exist, point and limit had to be equal. Okay. So let's jump down to do. A student showed his work below to confirm that the function defined below is continuous at x equals 2. So let's look at the student's work. It looks like first, to show that they're continuous at x equals 2, they're showing that the limit exists. So let's look into the work for the limit. The limit as x approaches 2 of f of x. They started there. They replaced f of x with the function. Everything looks good. I think you might notice if you substitute 2 in here, this is 4 plus 2, which is 6. 6 minus 6 is 0 on the top. If you substitute 2 in the bottom, 4 plus 10 is 14. Minus 7 times 2 minus 14 is also 0. 0 over 0 case. So we can't say that this limit equals 0 over 0. That's incorrect. But what we can do with limits is simplify it down. And maybe you'll notice that we can factor pretty quickly, right? X plus 3, x minus 2, I think will do the job there. 3 minus 2 is 1. And then in the denominator, x and x, 10's got to be 5 and 2, I think, and that adds up 7. Good. We can factor and cancel, and this gives us the limit x plus 3 over x minus 5. Now we can substitute in 2 for the x's, negative 5/3. That limit work looks really good. Then they said, okay, let's look at the actual point. So this was the limit existing. Now they're going to check to see if the point exists at x equals 2. So they said, well, here's my function. We reduced it. Now let's just find f of 2. And f of 2, they said, is negative 5/3. All right, doesn't seem too terrible. Last but not least, they said, okay, the limit equals the point, right? They took step 1 and step 2, and they set them equal to each other and said they both equal negative 5/3, so f is continuous. Except, it looks like there's no mistake, but there is a mistake. Do you see where? Hopefully you realize that this f of 2 on step 2 is actually the mistake. What they did is they substituted 2 into a simplified version of the function, and that is not what's going to give us the value of f of 2. F of 2 needs to come from this original function, and f of 2 is 0 over 0, which is does not exist, right? If it's a limit, like down here, that means do more. But if it's a point, 0 over 0 means there is no point there. So f of 2 actually is does not exist. There is no point at 2. And so, because the point doesn't exist, step 2 is the issue. Now, some people would say, well, doesn't that mean step 3 is also a mistake because the limit doesn't equal the point? And that's true, but that said, where did they first make a mistake? And as we read top to bottom, I think step 2 is certainly the incorrect part. Okay? This graph, because we were able to cancel out the issue at 2, would actually have a hole at 2. There'd be no point at 2 at all. All right, let's look at 3. Let f be the piecewise function defined below, at which value of x below is f of x not continuous. All right, so there's only going to be, let's look at maybe all the branches first, right? We can see these 5 different branches. We should notice that those 5 branches are all individually continuous functions, right? Parabola, horizontal line, cubic, horizontal line, diagonal line. All of those you never have to pick up your pencil. So the only time that we're going to get a function that's not continuous, maybe, is where the functions split apart. And it looks like there are 2 different options. We do something weird at 1, and we do something weird at 3. It's going to be one of those 2. So let's just quickly run through and see what happens for each of those. Okay. The first thing we'll look at is the limit and the point at 1. So let's find f of 1 first. F of 1, well, when you use x equals 1, that's going to be 3. A point exists. We can do the purple at the same time. If I want to find f of 3, looks like f of 3 is 0. The point exists for both of them, so we're off to the right start. Next, though, we need to find the limit. Okay, and so the limit here of f of x is going to be found by looking at the one-sided functions, or the one-sided limits. I'm not going to have a ton of space, so I'm going to cheat a little bit. I'm going to say the limit as x approaches 1 from the left side of f of x. Normally I'd put f of x, but let's see, the left side is going to be less than 1. That's controlled by x squared plus 2x. And I'm going to see, is that equal? Sometimes you'll see a question mark above just to show we're testing it. Is that equal to the limit as x approaches 1 from the right side? And the one that's in charge from the right side, this is equal to 1. This is greater than 1 right here, is going to be this cubic. So x cubed plus x squared plus x. Okay, as we substitute in 1, we get 1 plus 2. This whole thing becomes 3. Substitute 1, 1 plus 1 plus 1, that is also 3. So we found the point, we found the limit. They are both equal to each other. And so f of x is continuous at x equals 1. All right, so when they said it's not continuous, well, it is continuous at 1. We know the function's continuous at 2 because 2 is on this interval, it's in the middle, and this function is continuous everywhere. So if we pick a number somewhere in the middle where it's not endpoints, then it has to be continuous. So that's out. And the same thing 4. 4 is just a point on this line, which has no issues except at 3. So my guess is it's 3, but let's see if we can determine exactly why. Let's find that limit. The limit as x approaches 3 from the left side, which one's in control of the left of 3? Less than 3, that's this guy. X cubed plus x squared plus x. We're going to see, is that equal to the limit as x approaches 3 from the right side? And the right side is 2x plus 1. Okay, so doing a bit of math here, if we substitute in 3, I'm going to get 27 plus 9 plus 3. And over here, I'm going to get 2 times 3 plus 1. 27 and 9 is 36, plus 3 is 39. And over here, I get 7. 39 is not equal to 7. I'm going to put the not equal to all the way back through. So this limit does not exist. So this is our second criteria. We'd say the limit as x approaches 3 of f of x does not exist. We explained why right up above. Got to be 3. Not continuous. There's a jump discontinuity here when the one-sided limits are 2 different values. Okay, let's move on to our last page, problem 4, taken directly from a free response question from a few years ago. They want to know if f of x is defined as this piecewise function, is f continuous at x equals 3? Explain why or why not using the 3 criteria of continuity with correct notation. Okay, well, first things first. A lot of students will go through here and just forget to answer the question. They see those 3 criteria of continuity and they do everything great, but they never answer the final question, which was, is f continuous at x equals 3? Now we do want to do that at the end. This is the answer to the question. Sometimes students forget the 3 criteria. They're like, I'm just going to guess and maybe I'll get a point. So they just say, I'm going to say yes, f is continuous, right? continuous at x equals 3. And then they just skip the problem and move on. Unfortunately, though, what they've done here is given an answer with no supporting work. They did not enter into the problem. They didn't start the problem correctly. And if you just give an answer, this is called a bald answer with no work, and you don't actually start the problem correctly, you almost always get 0 points. Even if you're right, even if this is continuous, okay, you would not get points for the answer, right? You generally don't get points for guessing, but you do get points for entering into the problem, even if you forget the answer. So a lot of times a problem like this would probably be worth 2 points, where maybe 1 point is they started the 3 criteria of continuity. Maybe they used a limit. That's pretty common. And so if you started with the limit, even if you didn't get the rest, you'd probably at least get 1 to 2 points. Okay, so let's go into it. There are 3 criteria here. The first one, and you can go in any order, I always tend to start with the point though, is if we're continuous at x equals 3, the first thing I would find is f of 3. Let's see, f of 3, x is not equal to 3 here. Oh, x is equal to 3 on the top branch. So f of 3 is the square root of 3 plus 1, square root of 4. So f of 3 is 2. You could have just said f of 3 is 2 and you'd probably be fine. I like showing which branch you use though. Okay. Second, we're going to go through and we are going to find the limit. So what we're going to do is, and we're going to use better notation than before, we're going to find the limit as x approaches 3 from the left side of the function called f of x. And I think it's very important to discuss f of x here, and I'll explain why at the end in a second. And so we'll do the limit as x approaches 3 from the right side of f of x. Then we can put in the branch that we're talking about. The left side less than 3 is this top one, square root of x plus 1. And the right side will be the other one, greater than 3, which is 5 minus x. From here, you can put the answers. I mean, we already did the top one. We know that this whole thing is 2. And this one, 5 minus 3, is also 2. And so I'd say, therefore, the limit as x approaches 3 from both sides of f of x is 2. Okay. And last but not least, our third criteria, we'll switch colors slightly so it stands out, is we would say f of 3, that's the first one, is equal to the limit as x approaches 3, that was somewhat terrible, of f of x, and they are both equal to what value? They're equal to 2. Now, some nitpicky pieces here. First, if you just put this, you would probably not get full points. Do you see why? Yeah, it's because you didn't actually answer the question. They said, is f continuous at 3? Well, you showed there's a point, you showed there's a limit, you showed the limit equals the point, but did you answer the question? Do the graders know that you know that that means the function is continuous? So we should probably answer that, right? Well, you could just say, yes, f is continuous at x equals 3. That's fine. You showed all 3, you're good. You could say f is continuous because of that, and you would be fine as well. Nothing too bad. You can incorporate this however you want. I like to write them out as individual pieces. I've seen some students just write it all as a paragraph. They would say, yes, f is continuous at x equals 3 because this, and this, and this, and you'd be fine. Now, here's where I see students lose points. Sometimes students will do, and I'm going to take these 2 away, I'll put them back in a second. They'll do this. They'll find the one-sided limits and say that they're equal. And then in their conclusion, or even up here, they said, oh, the point equals the limit. Well, my question to them would be, I see clearly where the point is. Where did you show the limit as x approaches 3 of f of x? And they're like, right here. How do I know that's the function called f of x? You just use these 2 random functions. How do I know that this is the overall limit? Right? They might even keep this part down here, say the limit as x approaches 3 of f of x is 2, and my same question would still be, how do you know that? These one-sided limits don't talk about f of x. And so I think it is important to show that first step up here saying, we're going to investigate f of x from the left and f of x from the right. And once you're investigating those, then we can replace f of x, and now we have one consistent, coherent problem where we talk about f of x and finally state f of x at the end. All right, last couple problems for the day. Find the value k which makes each function continuous for the given value of x. You should incorporate limits as part of your solution process. Okay, if x is continuous at x equals 3, what's the value of k? Let's do the wrong way first. Wrong way is they might take this 3 and say, okay, this is going to be, and I will erase this, so just be ready, 3 squared plus 2, 6 times 3 plus k. And they'll say, okay, well, let's see, 9 plus 2 is 11, 18 plus k. Subtract 18 from both sides, k is negative 7. Cool. All right, here's the fun part. You are right. K is negative 7 here. However, if this was a free response, you almost certainly would not get any points for it. Right? They asked about continuity. They told you to incorporate limits here. And guess what you didn't use? You didn't use any calculus. Calculus is limit, derivative integral, or a theorem. And if you didn't use calculus, you probably didn't approach the problem in the correct way. So what are they looking for here? Well, ultimately, if we want this function to be continuous at a value of k, they're probably talking about the second criterion, which is the limits have to be equal. You could just up here say, well, let's just go through the full criteria of continuity. Let's find f of 3. F of 3 is when x equals 3, so that's this top part. 3 squared plus 2, 9 plus 2 is 11. Great, that point exists. It's good to check. Then we'd find the limit. And the limit is where I'd like you to focus, shockingly, your notation. So as x approaches 3 from the left side of f of x, okay, this better be equal to the limit as x approaches 3 from the right side of f of x. Okay, the left side of f of x is controlled by x squared plus 2, and the right side of f of x is controlled by 6x plus k. Now we can substitute in 3 once we've had those limits here, right? Again, I see many students go through and just say x squared plus 2 equals 6x plus k. Nope, not true. A parabola is not equal to a line. We definitely need to go through and substitute in that 3. 3 squared plus 2 needs to be equal to 6 times 3 plus k. We already said that this side was 11. 18 plus k. And see, now we've gotten back here, but we entered into the problem with that limit. And so we find that k again is negative 7. Now, if you really wanted to be good about it, you should probably go through and have one concluding statement, such as like f of 3 equals the limit as x approaches 3 of f of x, and they will all equal 11 when k equals negative 7. Realistically, though, they're looking for this point most of the time. All right, let's go ahead and look at b. F is continuous. What's the value of k? We get the idea now. I'll start with that f of 3 up here. Nothing too surprising. Which function? That's this one down here, right? So this one's a little different. We do k times 3 squared. So this is actually 9k. A point will exist as long as we have a value of k. But we can come back to that. Let's find our limit. So we'll do the limit as x approaches 3 from the left side of the function called f of x. And we want to make sure that f of x approaches the same on the right side. Because this is a piecewise function, the left and the right side are controlled by two different equations, 4x minus 1 and kx squared. There we go. Substitute in our 3 now that we've set up the limit. We want to make sure that these are equal when x has an actual value. 12 minus 1 is 11. This one is 9k. And so we find that k is 11/9. Just doing my nice due diligence then, we are going to see that f of 3 will be equal to the limit as x approaches 3 of f of x. What will the value actually be? Well, it looks like this one-sided limit was 11, so I think 11/9 will cause that to be 11, and 11/9 will cause the point to also be 11. And just again to show you what we're doing here, here are the two graphs. We had problem 5a, that's the one that we just did here, right? This is where we found that k was 6, I believe. And if you look at it, we've got the parabola on the left side and the line on the right side. We're approaching the same value. Or 5b, we have a line and a parabola. I replaced k with 11/9. And you can see as we approach 3, and I'll zoom out a little bit, we've got our line, which is in purple, and then this is actually our parabola. The parabola actually comes down and loops back around, but you can't really see that loop part because when x is greater than 3, it just kind of starts to look like a steep line there. Okay. All right, let's look at our last two. G of x is here. G is continuous at 0. What's the value of k? So we know G is continuous, which means the point exists, and it also means the limit has to exist. Okay, so let's maybe start with the point again. So if we're continuous at 0, G of 0 is right here. So G of 0 will be the cosine of k times 0. K times 0 is 0. What is the cosine of 0? That's the trig we need to remember. That's 1. So G of 0 is 1. All right, let's find our limit here. The limit as we approach 0 from the left side, now our function is called g of x, let's get that name correct, needs to be equal to the limit as we approach 0 from the right side of g of x. Okay. Now that we've got this going, we can actually replace g of x with the function that's in control. So less than 0, it's actually this bottom one this time, so be careful there. Cosine of k times x, there we go. And this needs to be equal to the limit as x approaches 0 from the right side of the natural log of x plus k. All right, let's substitute 0 into both sides. Cosine of k times 0, right, replacing x with 0. The natural log of 0 plus k. There we go. We already said that k times 0 is 0, cosine of 0 is just 1. On the right side, we can at least simplify the inside to get here. And now this becomes a question of how do we isolate k? Well, natural log is still attached to it. Do you remember how to undo natural log? That's right, we need to do e to the power of, so a little exponentiation here. Those will cancel, leave us with k. And e to the first power, well, anything to the first power is just itself, is e. And don't forget that e is that 2.718, so on and so forth. So we're saying k is the constant 2.7 something. Right? And again, wanting to do that due diligence, we would say, well, now that we found that, f of 0 is going to equal the limit as x approaches 0 of g of x, and those should both equal the point. I put f, that's awkward, g, and the point was 1. You can quickly check that. If k is e, the natural log of e is equal to 1. That looks pretty good. Graphically, looks something like this, right? Natural log is going to be, looks something like this, kind of like that downward facing parabola almost, and then cosine is the cosine wave, and you'll notice we have it over here, right? Natural log just had this part, and it actually has been translated to the left e unit, so it would go down something like this. And here's your cosine that's bouncing up and down. Definitely now we are continuous at 0. Okay, last one. What value will make this function continuous for all real numbers? Okay, well, let's just start the same way. It seems like might as well. We want to make this continuous, so I guess the question is, where is this not continuous? Well, they told us that this guy is in charge for every value except x equals 2. So it's showing you a graph right now. Here is -2. And whatever this graph looks like, it's in charge on either side. So I'm going to do this in green just so you can see. It does something over here and then kind of stops here. Okay? And then does something over here for everything else. Now, this would certainly not be continuous. What I need to happen to be at least kind of continuous is that this green part needs to come together, which to me means the limit needs to exist at x equals -2. So let's actually start by finding that limit just to make sure that it does come together. So I'm going to find the limit as x approaches -2 of the function f of x. Now you'll notice that I didn't do the left side equal to the right side. And the reason that I didn't do that is because it's the same function on the left and the right. It'd be pretty silly to set this function equal to itself. When you find a limit and that function is in charge on both sides, you just do a normal limit. So it's going to look like this. It's going to be the limit as x approaches -2 of the function, which is x squared minus 4 over x plus 2. So I'm just going to keep this left side about the same here just so we can kind of keep track of what's happening. On the right side, doing some mental math, you might notice if you substitute in -2, you get 0 in the denominator. And if you substitute -2 in the top, you get 0 in the numerator. So this limit is going to give us 0 over 0. So would you say the limit does not exist? Well, no, the point wouldn't exist there, but a limit in this case means do more. So what's the do more? I think we should probably factor, huh? X minus 2 times x plus 2 over x plus 2. Those cancel. So now we're just dealing with the limit as x approaches negative 2 of a much easier function, x minus 2. And I think we can even substitute in negative 2 now, right? We're just going to get negative 2 minus 2. So I'm seeing that the limit as x approaches negative 2 of f of x is negative 4. In fact, maybe I should update my drawing to make this look a little better, huh? So what that tells us then, if this is negative 4, 1, 2, 3, 4, that whatever my function is doing over here, it's going to come to negative 4. Then whatever it's doing over here is going to jump away from negative 4. Is that continuous? Well, no, that's not continuous because we haven't looked at the point yet. Okay, so I need to find the point, or what happens at negative 2. What happens at negative 2 is just k. So the point exists, but it could be anything. So how do we go further? Well, we know, finishing this off over here, that in order for the function to be continuous, a third thing has to happen. F of negative 2 has to be equal to the limit as x approaches negative 2. And luckily, we already found this right side, that's negative 4. The left side is just k. And so I think this tells us that in order for those two to be equal, k must be negative 4. Visually, what that means is that at negative 2, there is a point that has a y value of negative 4. And now we have a continuous function. If we take a look at my graph, it's going to be very different than that. This, when you reduce, actually becomes a line, right? It's just x minus 2. And so we have this function in red and blue. It's the same function, but I split it to show you that on one side and the other side, it's the exact same thing. And then we actually had to put the point right here, didn't we? Negative 2, negative 4, just like so. All right. Well, thank you for tuning in for continuity. Big takeaways for today are, first, you need to know the 3 criteria of continuity, 1, 2, and 3. You can do them in any order. You can write them out as a paragraph. I just like to keep them separately or separate. There's no particular order either. Some people do the limit, some people do the point first. And second, please be careful of your notation. Start the limit with the name of the function, then replace that with the actual branches of the piecewise function. All right, you're almost done with this unit. We only have 1 or 2 lessons left, and then we get to move on to our second big topic in calculus, derivatives. I'm excited to have you back next class.